Sergio, what's up?
Hello, hello.
How are you?
Very well. How are you doing?
How's the weather down there?
Oh, today was fantastic. Beautiful.
It's not bad here. Not bad.
Oh, it's like
Sun
it's,
feels warm.
today was more than 70, 75 degrees.
Oh, beautiful.
Very nice.
So, what your kids are in college?
Yes.
Yeah. Where'd they go?
Well, they're both virtual right now.
Yeah.
Luca is in Chicago and Julia is at UNH down in West Haven.
Oh, they're both virtual. And they live in with you?
No, they live in Wallingford.
Wallingford.
We left the kids behind.
They're lucky them, right?
Absolutely.
They must be good kids, you know.
Yeah.
They are good kids.
You don't have to worry about a party there every other night. Hey, Brendan, Daniel,
Bill, how are you?
excellent. How are you guys?
Good, thanks.
Hello.
How you doing, Daniel?
Hey, Daniel.
Mendoza, what's going on? There he is.
Sorry, no, this is off.
Got out of work, took a shower, feel refreshed. This is such beautiful weather out here.
I know. Isn't it? Like it feels
I
like
love it.
80, you know, it's like 45 degrees. It feels like 80.
Facts, because it hasn't been that warm in so long.
Yeah.
I
That's what
actually went for a walk yesterday. It was nice.
That's what the people down in South Carolina don't understand. The Brendan and Sergios of the world, you know, like when we get 45, it's like Miami Beach. You guys are in for a treat today. I'm telling you, you're in for a treat. You know how we beat to death hypothesis tests? Well, today we're going to do the same thing for control charts. Going to give Roy a minute or two, and maybe Sean Hassett. And I think we'll be done a little bit early today, because it's the control is about 80 slides, and I just feel like jamming 80 slides down your throat in 1 hour. Hey, Sean.
Hello.
So I figured I'd break it up into two. So we'll probably go a little bit, leave a little earlier today. Maybe 10 minutes early, something like that. And I got a little homework for you. And like I said, you know, if you're ever at a family function or a party and the subject of hypothesis test comes up, you guys will be able to plenty of information. And then today we're gonna do the same with control charts. So I'm gonna stuff you full of control start stuff. But we're gonna make it fun, because we're gonna actually do one or two. So I think I'm gonna
Remind
start.
me not
Okay.
to RSVP yes to your parties.
What's that?
So remind me not to RSVP yes to your parties.
Okay. I don't get invited to many. I don't understand why. I don't get it. All right, let me, I'm gonna start with the PowerPoint. And again, before we start, I think I'm gonna be sending you some data. All right, so I'm gonna give you from the beginning when I started doing my vital statistics to last Friday. And I'm gonna add in my blood pressure, the top and bottom numbers. So you can start kind of, I don't know if you guys had a chance to see how Rose, how she attacked the little special final presentation, but something like fun along those kind of lines. Which tools do you like? Get creative with it. I mean, obviously there's a lot of data. There's a lot of hypotheses that you can make up about the data in terms of seasonal, in terms of my age and weight, you know, during COVID, there's a whole bunch of stuff, you know, so I'll be sending you that. And again, we're into the control phase. And I think this is a lot lighter than what we've been doing. The plan is this week, the first half, instead of jamming 80 slides down your throat. And then next week, the other half, and then a review session for the exam, and then a take home 40 questions that you could probably do right now if you needed to, you know. So if that's okay, that's kind of what I'm thinking. I have to change Thursdays because I'm going to start teaching at Middlesex Community College, that Skill Up program that Olbricht's involved in a little bit. Next Thursday from 3 to 5. So I have to find I might have to go back to Wednesdays if that's okay. You know, Wednesday, say 3:30 to 4:30 or something like that. I know I'm gonna miss out on Roy, but all right, that's the plan. This is our 11th week together, and I really treasure it. It's been good. I enjoy it. All right, so here I'll start with the PowerPoint. We're gonna jump into the math practice, and then we'll finish up with a few more slides.
Yeah. When we go over all the things we went over, I think the hypothesis testing would be something that I would be interested in, like, going over again.
Yeah, and you know what? I don't think there's anything on the
Reinforce it.
exam on in terms of, but yeah, we'll go through the review and, you know, as we get the review, I'm basically going to go through the outline of the course, you know, like we have a constant, every week I show you what we're going to cover. So we go through it and kind of just a reminder, give you, you know, of what we covered, because we covered a ton of real estate in 10 weeks. So Stephen, how come you're so quiet?
Awesome.
On mute.
You're gonna help me today, because you know, Stephen's done a lot of work, a lot of reading, a lot of in terms of control charts. We're gonna get into the Westinghouse rules and things like that. So Stephen, feel free to fix me when I go off base, okay?
What did you say? Westinghouse rules?
Yeah, those are the rules. You know, if you get 3 above the upper control limit or 3 below, those are all
Oh,
called
is that what
Westinghouse
that's
rules.
called?
Yep. Special cause, common cause. Anyway, you guys are getting too excited, so I'm gonna start. What's up, Roy? Let's see.
How are you, Bill?
Excellent. How are you doing, bro?
All right. The links were all screwed up. I couldn't get on.
Did I screw it up?
It's all right. We got it.
All right. I'll make sure that's okay. All right, this is it, guys. We're down the stretch. So we're into the control phase. Define the problem, the objectives. What do we need to improve? Can we measure it? Think A3. Analyze the process, define the factors of influence, root cause, even though we covered root cause in the improve phase. Identify and implement improvements, and then assure the improvements will sustain, which is where we're at now. And it's about controlling those, remember that vital few, that why the process, what we want is a function of a bunch of X's, like a vital few, 3 to 5, 2 to, not a lot. And we want to be able to control those. And that's what this process, this part of the DMAIC is about. So we're going to get into types of variation, data collection, anything you ever want to know about control charts. You can see there's these statisticians, they just love doing this. You know, they hit you with a fire hose of different opportunity, you know, different types, depending on what kind of data you have. So I think we're going to cover all of the control charts that you might want to use with continuous data, and you know what the rules are in terms of when you would use them. And then I'm probably going to do discrete data next week along with the lean controls. All right. So that's control, and then we're going to be done. So SPC, a statistical method to monitor the performance of a process using control charts. And how many, if you guys use them? I know Stephen has. Anyone else use them at all? Control charts?
Well, I haven't used one personally, but I know we do use them and supply them for certain things that we do. And I've looked at them with very limited knowledge of perhaps what it's actually telling me.
Oh,
Yeah,
good.
we've seen those.
Okay. Yeah,
For thickness
Albert,
control
quite a bit.
mostly.
Yep. SPC can be used to distinguish between special causes, which we're going to talk about, and common causes of variation. Those are, you know, 2 types of reasons, causes of variation that we might have in our process. And it presents the voice of the process. In other words, if the process could talk, you know, the SPC is a way to look at, you know, those charts and say, are we in control? Is it predictable? All those things we're trying to get to. A process is stable, and here it is, when there aren't any special cause variation involved in the process. We're going to get into what that is in a second. the process is in statistical control, and I'm gonna take you over to the math practice, and we're gonna show, find out if my weight has been in control. The process of me maintaining my weight, which includes a whole bunch of other processes like working out, not overeating, whole bunch of things, right? The changes happening in the process are all due to random inherent variation, which is what we're going to call common causes. Those are things that, they're very difficult maybe to find out what they are, but they're the natural variation, why we don't land on the mean every single time, right? Why we have some fluctuation. And it also shows us that the process is stable when there's not any trends, unnatural patterns, and outliers in the control chart. And we're going to get into that in a minute, how a control chart can help you see some trends where things are starting to go out of control, unnatural patterns and outliers. So special cause, let me go back. Oh, common cause is also called chance variation. And it's the inherent natural variation in any process, right? If I say I'm going to cut a board 10 inches 20 times, well, I might get 10.15 or 10. And so what's that natural variation in the cutting process? It's the random background noise, which cannot be controlled or eliminated. Every process is going to have some noise in it. And the idea behind, the Six Sigma thinking is that we're going to continue to shrink over time the amount of variation above and below the mean. Its presence in the process expected and acceptable due to the relatively small influence on the process. I think John Peterson, who I think everybody but Daniel and Roy know, I think he had a really good analogy for this. It's basically, what if I measured how long it takes me to get to work, right? So, let's say, how long should you drive to work? 20 minutes. Well, it's probably not 20 minutes, right? Some days it might be 19 and a half. Sometimes it might be 22, whatever. And that's kind of the common causes of variation there. If I take the same route every day, if I plotted that over a period of time, I start to see that there's some common causes of reasons why my trip to work varies. All right. Special causes, on the other hand, on that same trip to work might be there's construction. I had a flat tire. Things that are assignable causes, unnatural variation of the process. I got behind a school bus, 4 school buses in a row, whatever. It's the cause of process instability and leads to defects of the products or services. It's the signal of unanticipated change, either positive or negative in the process. And it is possible to eliminate the special causes from the process, right? I change the way I go to work. I can make sure I pick up all the nails in my garage so I don't get a flat tire. There are A3s that I can do to make sure I get to work and eliminate these special causes. I think that was just a nice, neat analogy that John always used to use. He's for the other guys, he's a retired lean champion from Obrick, but I like the way he did a nice job with that. The variation factors, they're known. They result in non-random distribution. All of a sudden, I'll get something that going nice and straight line, and then boom. And I can explain that. I know what happened that day. Easier to identify, and there are opportunities for improvement right away. Now, the common causes are the unknown factors, and when I say unknown, they're a little bit more difficult to change, to detect. This, they're part of the process. Okay. And they result in a steady but random distribution of output around the average. And if you plot them, they usually follow, as you guys know, a normal distribution off the mean, right? A bell-shaped curve. So I get some little bit on the right, a little bit on the left, but usually if over time, they're going to follow a normal distribution. So let's talk about data collection for SBC for a minute. To collect data, to plot control charts, you want to consider, like, what's the measurement of interest? Is the data discrete or continuous, right? Remember, continuous is something that I can measure. Usually discrete, something I count. If you guys remember that from back then. We need to consider how many samples do we need? And that's kind of done a lot of times, with SQL, where we're going to take a certain number of samples at certain times during a run, a batch. How often do we sample? Where do we sample? What's the strategy? And how do we use the raw data collected or transfer them to percentages, proportions, rates, range? You're going to see a whole bunch of control charts where we use standard deviation to plot. We use the range to plot, things like that. A subgroup, this is important because this is going to help us determine which control chart we're going to use. We randomly select a group of items from the population of interest. The subgroup size is the count of samples in a subgroup. It can be constant or variable. Depending on the subgroup sizes, we select different control charts accordingly. And you're going to see that as we get into control charts. Rational subgrouping is the basic sampling scheme. And we're going to get into what that is in a minute. The goal of rational subgrouping is to maximize the likelihood of detecting special cause variation. In other words, the control limit should only reflect variation between subgroups. And the number of subgroups, subgroup size, and frequency of sampling have great impact on the quality of our control charts. So we want to have a good sampling strategy. The frequency of sampling in SBC depends on whether we have sufficient data to signal the changes in a process with reasonable time and cost. All right. So in other words, we want to sample it enough. We don't want to wait 2 months to sample something, because we're not going to know when the problem happened. The trail is cold. So it should make sense in terms of how often we sample. The more frequently, the higher costs it may trigger, obviously. And we need the subject matter's experts. That means the person who's doing the work on the nature and characteristic of the process to make good decisions on sampling frequency. So control chart structure and rules. And I'm just going to touch on this and then let's go do one. Control charts are graphical tools that are used to present, analyze, and monitor performance. They're used to detect special cause variation. And they determine whether the process is in control, whether it's predictable. That's the goal, right? Is my process capable of what I want it to do? And then is it stable, which is code for it's predictable. And this is what we're going to build here. This is a basic common run chart with a mean. So this is the mean of all my sample set. And now every day or every shift or every hour, I'm going to go sample it and measure and plot it in a line graph, a 2D line graph. And then you're looking at what's above and below the mean. This is the variation. So again, the green is the mean. The vertical axis is the value intervals. The values themselves are the red dots, and then horizontally we have time. So this would be, you can do Monday, Tuesday, Wednesday, Thursday, Friday. You can do hour 1, 2, 3, 4, 5, whatever that time frame is going to be.
Hey, Bill,
Yep.
how is this different from the one we did last week or 2 weeks ago, the Pearson's, I believe it was called?
Oh, the XY? Yeah,
I mean, there was a mean, and we were finding the points were too far away from the mean.
Yeah.
To me,
that's a great question. That's a great question. What we're really thinking about there was, can we correlate? Is there any correlation between two sets of data, right? And the reason I use that XY plot is I could see visually without doing the Pearson R calculation, if they're right along the line or if they're way off the line. That scatter diagram gives us a picture of correlation, Sergio.
Correlation, yeah, you're right.
So here what I want to see is my process in control? Is it very consistent day to day? Right.
I get it. Thanks.
Yeah. And this is what we're going to make today, right now. I have an upper control limit, and usually the upper control limit is going to be 3 standard deviations above the mean. All right. Believe it or not, these statisticians, bless their soul, they have, for some of the types of control charts we do, in order to get that upper control limit, we have to go to a chart, right? They love charts, and the chart is based on my subgroup size. And it's a constant that you put in there. But for us, most of the time, we're going to start with 3 standard deviations above the mean and 3 below the mean, and those will be our upper and lower control limits. All right. And all right, I think I'm gonna come. All right, let me go. I'm gonna jump into the math practice, and we'll get back into Western Electric rules.
So it's
There's
kind of bell curve.
What's that?
It's kind of like the bell curve with 3 standard deviations each way.
Yeah, and I think on that slide, when we get back to that slide, you'll see that for that slide, you know, we put a bell curve on the, because that's exactly right. Nice job. Way to pick that up, Daniel. So here's our math practice. Everybody see it okay? I got, I don't know, I just randomly picked the first half, my weight values, January to June, the end of June, 2018, just randomly. All right, so I'm going to use that as the data set. So the 2 things I need to know right off the bat when I'm going to build a control chart is 1, the mean, which we know is equals the average, click, of that data, hit enter. So my average weight is 186. And then I want to find out the standard deviation, which is how much deviation do I have from the mean? What's the number that I can get that gives me a number that shows me how far I am with this set of data away from the mean? So I'll do equals standard deviation. And do I use P or S? There's 2 of them here, P and S. Which one do I use and why?
S.
You know, with a sample, right? So you
Yep,
want to.
excellent. Yep.
S.
Yep, so I'll pick the S one, and I'm gonna take that same set of data, and you can see that my standard deviation is 1.359, all right? Now what I need to do is go over and I'm gonna build 3 columns. 1, the mean, I'll label 1, or just sometimes this is just called the control limit, the mean. If this is like stuff you guys have already done, let me know, okay? But I figured I might just take you through it. And then I got to figure out what my upper control limit is and my lower control limit. And the way I do that is first I'm going to take the mean, and the mean is going to be equal to cell I2. I already figured that out, right? So you see that's in there. Oops. Duh. So there it is, 186.75. But what I need to do is I got to put a $ between the I and the 1. Because watch what'll happen if I just take this thing and drag it down by itself. See what I get? Because it's taking, it's using the weight number, compare, you know what I mean? So what you have to do is to prevent that from happening, to be able to drag it, I got to put $ in. So when I do equals I1, if I put a $ between the 2 of them, just the way Excel works, I still get my 186, but now when I drag it, everybody's 186. Now my upper control limit, the logic there is it's going to be equal to my standard deviation, I'm sorry, my mean, plus parentheses, my standard deviation times 3. So times asterisk 3, close parentheses. All right, so my upper control limit is 3 deviations north of the mean. So 190 pounds is my cutoff, right? And as your process gets more and more improved and more stable, then I can make it 2 standard deviations above the mean. All right. And the same thing, I have to go ahead and I have to put $ between the I and the 1. I have to put $ between the I and the 2. And there's my number still. And now I can drag it down, and I got to do the same thing for the lower control limit. Lower control limit is equal to the mean plus, minus the parentheses, the standard deviation times 3 parentheses. That's 182 pounds. All right, so I'm going to take the $ and throw them in there again so I can drag them and have them make sense. and that one. And I could drag them. And now all the hard work is over. And now I could do a control chart, just go insert. And we're gonna do a 2D line chart, one of these. Before I do that though, I gotta select my data. So I'm gonna take the weight. I'm gonna take the mean, the upper control limit, and the lower control limit. And then I'm gonna go to that 2D line chart. And there it is, all right? So as simple as that. And I can go ahead and label it the way I want it, change the title, whatever I like. Here's the lines, the blue is my weight, dark blue, etc. You guys have probably, maybe have done this before, but I thought it was worth a review on how to do a control chart. So if I have data, I could do a control chart.
So I thought it was supposed to be like scattered, like with the dots instead of the lines in the middle.
For a control chart?
Yeah, I thought it was supposed to be like dots, and then it, you can see when the dots are above or below the mean.
Yeah, I think that's it's similar to what Sergio had the same thing, same thought, and that we're going to use a scatter diagram when I want to kind of understand if I have two pieces, is my data correlated? Like, in other words, does my weight and my pulse rate matter? Are they, you know what I mean? Is it predictable? Does one go up? Is it positive? Is it reverse? And a scatter diagram, by looking at that, I'm looking to see visually, how far off that mean line is. That perfect correlation is. So this is a mean line here. This is not a correlation line, right?
Yeah, I know. I'm just saying like the same thing you got there, but just with dots where the points are.
Yeah, you can do that too.
You
You
could
can do
add
that
the
too.
dots to the chart. You would just have to change the.
Yeah, you
Oh,
can
can
do
I
dots.
change it to do that? Can you show me how to?
Go to dots.
Yeah.
Like if I want to do a scatter diagram, I never
I
did
think
it.
if you go back to the
He's
slide.
just saying put dots on the data points.
Yeah, I think it's just showing.
Oh
you
yeah,
the-
okay, yeah. You show data points.
Yeah,
Mhm.
yeah, there you go. So
Is that what you meant?
Yeah.
Okay, cool. All right, so that's basically like right now, I think one of we're looking at productivity over at Atlas, on a weekly basis, sales per labor hour, and they're interested in, so they've been collecting every week dollars shipped divided by hours worked, and they're plotting it on a control chart. But it's very, very useful tool, very easy. All right, so let's get into the alert rules, the Westinghouse rule. Let me switch back. All right, so there's our elements, simple. All right, the Western Electric rules are the most popular decision rules to detect unnatural patterns. And this is how we see special causes on our control chart, right? What triggers us to say, wait a minute, time out. What's going on here? There's something screwy going on, right? And there's unnatural patterns in control charts, like outliers, trending, cycling, autocorrelative, and mixture. The process is in control if all the data points on the control charts are randomly spread out inside the control limit. So what happens when I start to get data outside those control limits? So test one. So there's a set of rules, right? 1 point outside the control limit, which is more than 3 standard deviations from the mean. So if my weight all of a sudden was 194 pounds, right? What does that tell me? Well, I should be able to explain that special cause. It could have been I ate at the China buffet 3 days in a row or something, or I had pizza every night, or I decided not to work out and drink a lot of beer or whatever. Like I need to be able to, the whole idea is I need to be able to explain these special causes. And it's typically known as an outlier because I don't know what my control chart's going to look like for all of the time I've been keeping track, but you might see, some outliers there, and they're explainable. Like one of them you'll see is during COVID, I lost 8 pounds, right? So every Friday I'm checking still. So you're going to see outlier there, but at least all right, that's COVID. We're going to get back on Actually, I want to stay there. I maybe move the line down, but so the outliers, one outlier. Test 2, 9 points in a row on the same side of the center line. All right, so if you count these up, there's all of a sudden there's my mean, and then I'm doing the control chart. I see 9 points in a row below the center line, my mean, right? And identify situations where maybe the process has temporarily shifted. Maybe, that might be, let's say, like I had COVID for 11 days. Let's say it went, and let's say I weighed myself every day and it was still below that lower control limit, then I would be able to explain it, right? And then it would get back on track. Test 3, 6 points in a row, steadily increasing or steadily decreasing. So just visually, by knowing these rules, you know when to start questioning your process. Like, what's going on? All right. So 6 points in a row, either going down or going up. Test 4 is 14 points in a row that are alternating up and down. It indicates some kind of a cycle, in your process. And 5 is 2 out of 3 points in a row, at least 2 standard deviations from the center line. All right, 2 out of 3 of my readings in a row, because don't forget, this is time on the bottom, right? 2 out of 3 are at least 2 standard deviations from the center line. And I apologize, I didn't mark the 1 and 2 standard deviations. You can actually put those lines into, and how you would do it, right? When you do that, remember the calculation I did where I dragged the data? I just have to do it with mean plus parentheses standard deviation times 2. And then I'd get another line, right? And then minus 2, then I get another line on that chart. Is that, you guys got that in terms of how to add those lines? Rule 6, 4 out of 5 points in a row are at least 1 standard deviation from the center line on the same side. All right, so if I see this, my control chart, and all it is it's a red flag, right? It's I want to look a little closer. I just don't want to, like, if I do control charts, do I just keep plotting data, everything's fine? I want to start to look for trends before they happen, all right, and start to address it. Maybe it's, maybe in this case, it's not cyclic. Maybe it's not, it's just random still, but it gives me an alert. All right, maybe there's something going on here. Test 7 are 15 points in a row within 1 standard deviation from the center line in either side of the center line. And this kind of, it indicates a change in the level of variation around the process main, right? It means that I might be able to tighten down my upper and lower control limits. Maybe we're getting better. Stephen, is that one right? Did I get that one right? The 7 in a row?
I'm sure they're all right. The ones that I got out of that book, that Graben book that I was reading, were, I think he had like 4 different ones, and they were maybe slightly different, but close to the ones you're doing. It's the, basically the same kind of thing, is that you're looking for signals for times when you should go and see that maybe this is not common cause variation. Maybe there's a special cause going on here that we need to go look at, or maybe your process is shifting.
Yep.
And then
it doesn't necessarily mean, you're going to react to every shift, right? We're not going to go do A3. So this kind of gives us like some kind of an idea.
I want to go, look deeper.
Yeah. These are the rules of the road. Rule 8, this is the last one. 8 points in a row beyond 1 standard deviation from the center line on either side of the center line. All right, 8 in a row. Well, test 7 indicates a narrowing of variation. Test 8 indicates an increase in variation. All of a sudden, we're plotting and we're nice and neat, on both sides of the center line. Then all of a sudden, we see this. Well, signal, we're running out of argon or something. I don't know. The argon's jammed, or I don't know what it is.
So I feel like that would kind of be like maybe you're working on a power press and then the parts are coming out good, you're checking them, and then one of the tooling like breaks and then you realize like variation after that.
Yeah, cracked or something, who knows, yeah, that's exactly
Something
right.
gets stuck or
Yep. Or
okay.
it could be simply, that we have a new person measuring, or a new
That too.
technician.
Yeah.
Yep.
I feel like this is really good for like power press and force slide. That
Yep.
stuff's really great for that because there's such volume,
Bill, if we were to create a control chart from like a run chart of data, like let's say for instance your weight, right? Is there anything within Excel or any kind of software that keeps track of these 8 rules and identifies them for you that you know of, without you having to go through and kind of search for these patterns?
I have to get back to you on that.
I mean, I could look. I was just curious.
I'm not aware of anything other than, kind of knowing, you know what I mean? Like,
Yeah, just looking through. I just, if you had like huge amounts of data, like hopefully someday we may have from like a SaaS system or something like that, and we were looking up trends on a mill or something like that, and we had months and months worth of data, rather than kind of going through and looking for these signals, because there are 8 of them, and it's not easy to keep them all. Start counting. Is it 8 on one side and 3 on the other, or is it, just curious if there was anything like that with.
like, I want to find out, because what you're talking about is really like an and-on system.
Yeah,
So
so that's all you basically need to do is keep the run chart in this kind of control chart setup like this, and then would it highlight areas that it deemed to be signals based on these rules? And I'm sure you could create something.
Yeah, probably Brendan. Our accounting guy, finance guy, math guy. I mean, it's got to be some equation, though.
It would be pretty cool if you had tons of data you were trying to see patterns in. If it would just kind of highlight them for you.
Yeah, I got to find out, because that's really brilliant. You know what I mean? Like an and-on system that says, "Hey, listen, you're violating Rule 3 or like one of the rules."
Well, if it doesn't exist, guys, this is the next good app idea.
Yeah. See, if Daniel asked that question, then I'd assign it for homework. Guys got to develop a mathematical formula for Excel so we can alert us.
Yo, you could do it, Steven. You could get rich.
He's already rich.
New system.
If you could combine, if the data you're seeing in that control graph is somehow correlated to other data, and you can see a spike in this control graph and then compare that to spikes in other data points, can point you in the right direction at least.
Yeah.
Like we have like some kind of another sheet that it refers back to that shows that number above or below.
Yeah, say it's speed.
See, I told you, Brendan. So control and stability. So if no data points fail any test for special cause, the process is in statistical control. That's all that means, okay? If any data points fails any test for special causes, the process is unstable. So it fails any one of them, all right? And again, it's just a trigger. Process stability is the prerequisite of process capability analysis. And some people will tell you it's also a prerequisite for continuous improvement, all right? My argument has always been, do I want to do improvements or wait? And, like what comes first, the chicken or the egg? I'd rather get especially when I need to make money, shift, feed my family and all that. I want to make improvements and then remeasure. I don't want to wait until I get things in control. And you set a periodic time frame for checking control limits and center lines. You do that. You just be aware of those rules. And I'm going to find out if there's a tool.
It is helpful though, Bill, to get rid of as much special cause as possible before you start trying to.
Yep.
A good example of this is, I think probably most of the Albrecht folks here know that we're trying to make some improvements on the BD products and stuff like that. So we're having coil size issues because we're breaking coils at different places and then they don't meet minimum coil size for the customer. So You know, here we are doing this, and then we had 2 days in a row where on one of the mills, actually the new mill, one day there was a faulty gate that led to the machine e-stopping, and then we had to cut the coil. And then the next day, somebody came over to talk to the operator and put his hand on the control panel, hit the e-stop button, and they had to cut that coil.
Yep.
So, you know, you're kind of shooting yourself in the foot here when you're trying to, you know, we're trying to make changes to the process, which would get the common cause variation down or shrink that window. But we're tripping over special cause stuff, right?
You know, I think I'm going to go back to John Peterson's analogy. You know, it's in other words, let's say I got a flat tire on my way to work and I arrive late. I'm not going to go out and do an A3 and decide that I'm going to leave my house, you know, half an hour early every day now in case I get a flat tire, right? I want to get that special cause taken care of, right? And get the root cause with it. But I'm not going to go and change my process. You know, same thing with think of any other special causes that might, an accident, for example. You know, I got to work 20 minutes late. Well, I'm not going to get up 20 minutes earlier, eat breakfast 20 minutes earlier, shower 20 minutes earlier. I'm not going to change my process for a special cause. So I think that's another way of thinking about it. You got to make sure you tell John that I was talking about him again, Stephen.
We just took all the e-stops out so that we're running unsafe, but there's no more cut the coils, right?
Yep. So I think this is about manual construction of control charts. I'm gonna we don't need to do that because we just did it, right? We just did it with some math. And the big thing is, you know, selecting the type of control chart, which we're gonna get into. And here's the selections, right? So I have either continuous or attribute or discrete. Discrete and attribute are the same thing. And what we're gonna follow right now is the path from I have continuous data. We're going to look at the subgroup sample size, and then we're going to pick one of these 3 charts. And I'm going to kind of breeze through it. That, like, you know, you'll see subgroup sample size is 1, 2 to 9, and 10 plus. So you use different, and these are probably charts that you're not going to use all that often. You'll see that they're a combination of 2 charts, really, right? Where I'm looking at either. Let me get into it. So the IMR first. So it's called the individual moving range chart, or IR, and it's for continuous data. So again, all these charts are for data that I'm measuring, all right? Not discrete data, which is counting, either, you know, defectives or defects. We'll get that next week. But eye chart plots an individual observation as a data point. So that's what we just did, right? We did the eye chart. The MR chart plots the absolute value of the range between 2 consecutive points, right? So how far away are they? So we're going to look at the range on that. The eye chart's valid only if the MR chart is in control. And it's the most sensitive of all charts to changes. Again, I'm not sure. I've never really done any. I just do a basic eye chart all the time, but I think it's good to have in the back of your mind. This is the most sensitive of all the charts to changes. And when it's really important that we don't have a lot of variation. And the underlying distribution is normal. And here's the formulas for both charts. X1, the sum of X1 divided by my sample size and the control. We just did this in Excel. In the MR chart, now we're looking at the range. So we're looking at the difference between successive, you know, subsequent data points. And the MR chart, as you can see, this 3.267. I'll give you 3 guesses on where that comes from. A table. These statisticians love their table. This is what it would look like. So it's not 1 chart now, it's 2. The eye chart is right here, the one we just did. The MR chart is, and there's our mean right here, just exactly what we did with my weight. And now the MR chart is a moving range. Like how much are we seeing, what kind of difference are we seeing between two data points? So we're measuring how much difference between points. Make sense?
Wait, can you say that again?
Yeah,
doesn't make sense to me. I'm sorry. To me,
Yeah,
the two
so
charts look
basically,
the
this
same.
is like anytime I want to really tune in with a microscope how much variation I have in a process, I might use an IMR chart, which is really two charts at once, right? I'm not only going to do what we just did with my weight on the top chart, but I'm also want to know from data point to data point, from sample to sample, what's the range? What's the difference there? I'm going to plot that. All right. I'm going to plot because I don't want to see a lot of difference from sample A to sample B to sample C. So I'm going to measure that difference, that range, and plot that. Not the point it's like on the top one, I'm just plotting my weight, right? Now down here, I would plot my weight 185 1 week, 187 week. Well, that's 2, right? The range. Remember the range of sample points? And the same thing with the following week, the following week, the following week. So what I want to see down here is I don't want to see a huge difference between 2 subsequent data points.
So basically that lower graph, the moving range chart, is referring to the top chart, and it's a signal of how much volatility there is to the top chart, how
Exactly.
much distance there is from point to point.
Yep. Again,
So
don't get
the
too
top chart
caught
is
up.
jumping around a lot. The bottom chart is going to reflect that, basically. So it's telling you, it's kind of telling you how stable the top chart is acting, I guess. Maybe that's not the right word for it, but it's if you have a lot of change in the range between one point and the next, the bottom chart is going to reflect that and show you that. It's going to kind of magnify that.
Yeah, like the top chart saying, hey, everything's in control, we're good to go. And if I really need to fine tune what I'm looking at, a signal or variation, I'll do the MR chart and it tells me the same exact data. I have 2 outliers there.
And that's telling you basically that the data points right above it on the top chart, you can see that one data point down to the next that's dropping all the way down to the control limit, at the lower control limit. It's telling you there's a lot of variation there, and then when it jumps back up.
Thank you, Stephen.
I don't know if that helps or not. It's just,
Help me. And the X bar R, it's a control chart for, again, continuous data with a sample size. This was a sample size of 1. This is a sample size of 2 to 9. And it plots, the X bar charts plots the mean of a sample as a data point. And then the R chart plots the difference between the highest and lowest values within a subgroup as a data point. There's the calculations for both of those charts. So both, again, and what I'd like you to take away from this is like 90% of the time, we're going to use an eye chart, what I just did, for most of our processes. In this case here, we want to take a finer look at, our eye chart's good. We can't tolerate any variation at all. We might use something like the X bar R. So the X bar R chart, same thing. It's a combination of 2 measurements, one being the sample mean on top, and one being the sample range again. Now I have 3 to 9 samples, not just one. And now I got to find the range of those 3 to 9 samples to plot on the bottom, the difference in subsequent sets, right? So let's say I take 5 samples from 5 different machines, and I'm going to build a control chart. Well, that's when I would use this one. And the way I would do it is I'd look at not only the mean of all those samples, but then I'd take those 5 and look at the range of the differences between those samples. This is not on the exam, so this is and then the X bar S chart. It is a control chart for continuous data with a constant sample size greater than 9. All right. The X bar chart plots the sample mean as a data point, and then the S chart plots the standard deviation within a subgroup as a data point. All right. The X bar is valid only if the S chart's in control and underlying distribution is normal. There's the formulas for them. And again, for the top one here, we have sample mean, and this is, again, we're taking greater than 9 samples. And down here, we have the sample standard deviations. So the standard deviation between the samples. All right. Oh, it's 5:05. I think Brendan, hey, Brendan, you still there?
Yep, I'm here.
We're done.
Nice.
I know he said he had to go at 5. So I didn't want to get into, the discrete data control charts. We'll touch on that next week. And then we'll get into the lean stuff and then done. The homework I'm going to give you is, I'm going to send you a set of data to do a control chart, if that's okay. If you guys haven't done one, just like I did, I'll give you another set of data. And then just send it back to me. Just want to see if I taught it well enough. All right. Thank you, guys. Great seeing you.
Thank
Thanks.
you.
Thank you.
Thanks, Bill.
Have a great
Thanks,
night.
everybody.
Have a great
Thank
night.
you, everybody.
Bye, everyone.